Very good morning. Today we are going to start with a fresh topic, so-called ordinary differential equation, and which fall into your fourth unit and as well as in fifth unit, last unit. Okay. Before starting, I can comment on the uh, uh, what uh, what was unanswered during the last lecture. It's like how to find the surface area by using the single integral of a in Cartesian coordinates. So you can similarly you can transform to the polar coordinates as well. Okay. So if you take an example here, I will just let me have this xy plane, and you have, let's say, this is some curve y equals to f of x. And if you revolve it about the x-axis, so what you will get is we will get something like this. If you revolve about the x-axis, you will get a shape of some called, means like mathematically it is also known as a cylinder. Okay, it's not a right circular cylinder, but it is called a cylinder. Means where you are stretching, means like along the x-axis. Okay, and by following the curve y equals to f of x. Okay, right. So now what we are interested in, the surface area of this cylinder, in other words. Okay, so what you can do is you can let's say this is the point A and this is the lines from A to B, and you can go for the approach what we have done for the Riemann integral as well. Okay, so what you have done is you have divided into the partition. Okay, so A equals to x naught, this is x1, this is x2, this is x3, and so on. Let's say this is xn minus 1. So each of length is, you can say, delta x is delta xk is xk minus 1. So you have subdivided the interval into n sub intervals. Okay, so the partition k is equals to 1 to n. Okay, and whose length are same. So delta x, they are equidistant. Let's say let delta xk is or you can say this delta xk is equals to delta x sum for all xk. It's a small element, you can say. Okay, so what you can do is let's have here this is x3, let's say. Okay, and let's say this is and so on, and you are having this xk minus 1 to xk. Okay, so over this interval you will see the part of the surface if you draw it. Okay, so if you draw, so it is like, okay, and if you recall what is so this will be, so if you look at in the very small, with the small element here, so delta x length, so it's going to be, you can consider this as a part of a cylinder, right? Circular cylinder, what you know. Okay, and so this length you are having is this is the height is y equals to f of x, and this is a very small element, so it's going to be straight line, and that you can assume that that's going to be delta x of length. Okay, right. So now, if you recall, what is the surface area of the cylinder is 2 pi rh, if you recall. So what was the r is the height, the radius. So radius is y equals to f of x, so that is going to be 2 pi y into h is here delta x. Okay, or sorry, this is not delta x, this is going to be some delta s. How will you obtain is delta s here is, so because this is going to be this delta x and this is going to be delta y. So let me color it with the let me have this is here. So let me have it color here. So this is some delta S. How will you obtain this delta S? Is going to be this right circular selector, right angle triangle where the base is of the length delta X and the perpendicular has the length is delta Y. So this is 2 pi y dx delta S. Okay, so now what is going to be is this is 2 pi y, 2 pi y, and what is delta S is square root of delta x square plus delta y square. If you recall, that's a you can say this is delta S whole square is equals to delta x square plus delta y square, Pythagoras theorem. Okay, now this delta x and delta y you can replace it by some dx and dy, and so this is a discrete one. So if apply the limit, so then it will give you the surface area is going to be integration a to b 2 pi y square root of dx square plus dy square. Okay, now this is ds. Okay, so that dx. So now, so this is when you are having revolving about the x-axis. Okay, now similarly, if the curve is revolving about the y-axis, what will be the possibilities? So then you will have the curve is 2 pi x times delta x, and that's going to be the same. So when you have the revolving about the x-axis, you have this 2 pi y here. And when you have revolving about the y-axis, you will see that that's going to be 2 pi x, because you are going to take here x is a function of y. Okay, now you can further write in the form of integration a to b 2 pi y times square root of 1 plus this is dy by dx whole square, dy by dx whole square, and dx square is out, so that's going to be integrate, because you are going to integrate with respect to x, because you are known that y is a function of x. You are treating y as a function of x. So as a function of y, that the situation means you are taking dy out and you have dx by dy whole square plus 1 square. Okay, now you can write the formula in form of polar form. So polar form says that x equals to r cos theta, y equals to r sin theta. So you can replace y by r sin theta. Okay, and you can certainly replace this dx square by square plus dy square by d theta square. Okay, and you take d theta. Okay, so you can certainly get the polar form from there. So by replacing or we are substituting, you can say pi equals to r sin theta and y equals to r cos x equals to r cos theta. Okay, this is for polar form. Also you can go for the parametric form in the same way. So if you have x equals to x of t and y equals to y of t, then also you can write formula. You can also write these formulas, and you certainly require the limit of t as well, so alpha less than equals to t less than equals to sub beta. So replace y by y of t, dx square, you divide by dt square, here dt square, and take out dt. And limit is alpha to beta. Okay, substitution. Okay, so that will give you the surface area in the form of parametric form. This is in the form of polar form. So likewise, you can extend this result now. Okay. So this is what, and whatever I explained at present this here, you can similarly get the volume of the solid of revolution as well in the same way. Okay, so the volume of solid of revolution is going to be pi r square h. So if you require, if you know that cylinder has the volume is right circular cylinder has the volume is pi r square h. Okay, so from there we have derived that volume of solid of revolution. So h was here delta s in the case of this is for surface area, and in the similar manner you can certainly get the volume. For the volume can be for the small element, means like in the you can say in the interval from xk minus 1 to xk is going to be approximately pi. R square is y square, h is the delta s. Okay, so that's going to be pi y square root of dx whole square plus dy whole square. And now if you want over the integration over the entire interval a to b, so this is a continuum case. Okay, so means you are going to apply the limits, because you can take as small as possible the length. Okay, so then total volume is going to be integration from a to b pi y square times this square root of dx square plus dy square, so dy by dx whole square dx. So now it is means like based on the requirement, like y is a you are taking y as a function of x. Okay, it's revolving about the x-axis. So if you are going to take y is equals to x equals to f of y, and you are considering and the solid is revolving about the y-axis, the scene will change here, pi x square times square root of dx square plus dy square and so on. Okay, so this is the same way, same technique what is Riemann has approached with. Okay, so Riemann has approached with the dividing the area into the area of rectangle, but it is considering it is dividing by means of partition a solid into a, you can say cylindrical things. Okay, right. And you are using the fact that what is the surface area of the cylinder, right circular cylinder, and what is the volume of the right circular cylinder, using that fact, and then you are integrating over the entire interval. Okay, right. Now we are going to start with our OD case. So I have already posted to you that what will be the main textbook is going to be by Simmons. Okay, you don't need to worry about this. This should not be there, because you are not working with the partial differential equation, so it's not going to be part of your course. Okay, so this is not going to be part of this. So you are going to work with this book. Okay, and I will also mention you which chapter we will follow. Okay, right. And for reference, you can go with the Erwin Krejcik book, Advanced Engineering Mathematics. Okay, and then this is not the part. This is also not the part. This is also not the part. So we have two books here. So one is Erwin Krejcik and another is the Simmons book. Okay, so you can refer any one of them. Okay, but the notations mainly will be followed with the Simmons one. Okay, right. And another Erwin Krejcik is a very standard book for engineering mathematics. So it covers many things. Okay, means many topics in the engineering. Okay, so if Indian edition is available, so you can also buy it. It's for your future purpose, since you are from mathematics. Okay, so it will give you numerical methods and so on. So many things will be there. Okay, and it has a nice collection of problems as well. Okay, it's a very colorful book as well. Right. Okay, so the very first question I think I need to answer is, why should we use the differential equation or derivative? Okay, and what do you mean by a differential equation? I hope you have already aware about this. Okay, maybe in your intermediate sessions as well. Okay, at least with linear differential equations or linear differential equation. Okay, some of the very special cases. Okay, now this is the physical significance, or you can say the geometrical interpretation sometimes also attached with this, the derivative. So we are only stick with the function of single variable. Okay, so y dash equals to dy by dx. That's a we are going to use the notation. So you can say this is notation. Y dash we are going to use as dy by dx. Okay, so y double dash means second order derivative, d square y by dx square. Y 3 prime will be there, so then you have t cube y by dx cube and so on. Okay, so with how do we interpret it is as this is going to be rate of change of y with respect to x. Okay, so it is like how many changes there whenever x is changing from, okay, x is changing dx, what is the change in y? Okay, so that will given by dy by dx. Okay, right. Okay, so now I hope the very first application is Newton's second law of motion. Okay, so which is given by mass into acceleration equals to total force. And this is a part of your as well as physics. I don't need, I don't think so it is need to be explained here much. Okay, so how it occurs is, so if you have a body of mass m, okay, which is falling from the, you can say, 5th floor or 6th floor, only working the force is the right now is falling freely, okay, and only the working force is the gravity. So velocity is the rate of change of displacement with respect to time. Okay, and certainly a is equals to dv by dt, which is nothing but the d square x by dt square. Okay, so if you have a body of mass m which falling from at any very highest level, you can say, and with acting force is gravity. Okay, so this second law of motion tells you that the equation means what will be it satisfy is d square x by dt square equals to total acting force is mass into gravity. So you have the only equation is d square x by dt square equals to z. Okay, and you know g is the gravity is the constant, okay, independent of time, and whose solution, okay, whose solution you can find out by some method which you can say you can integrate 2 times here and you can find x as well. Okay, now suppose there is interference of the air. Okay, so air exerts here resistance here. Okay, so what will happen in that case is, what do you mean by it? So if we assume that air exerts a resisting force proportional to the velocity, so let's consider this case, resisting force proportional to the velocity. So it's going to be velocity. So here, so y is you can replace it by x. So from our based on our earlier previous notation here. Okay, so then what is saying is air is exerts a resisting force proportional to the velocity. So velocity is dx by dt, and it is proportional to, so it's going to be multiplied by some constant, and it is going falling down, so that's why the negative sign will be there. Okay, so you will total force is the mass into gravity minus this force. Okay, and that will then you will get a, this is a right now I can comment is here is this is a second order differential equation. Okay, right. So there are also many other applications in electrical fields, means ferromagnetism. So there you will find some second order PDs and all. So we are not going with that. Diffusion and wave motions as well. Okay, so that's also second order PDs. So but for mentioning right here application the differential equations in further engineering field is you can mention them. Okay, so but our concern in this course is not solving these problems, diffusion and wave equations and so on. Maybe in the future you will see that. Okay, right. So now, so general ODE of the nth order is given by this. Okay, now see what it's a general function f of x comma y comma dy by dx comma d square y by dx square. So it's a function of, you can see this is a y to n, so this is going to be n plus 2. Total numbers are n plus 2. Okay, so don't think that this is a n plus 2 variable problem. Okay, so it's like, so if you go back and this here, so I just, so this is in the form of, you can say, a some function of t comma y dash and comma y double dash equals to 0. So if you write some expression equals to 0, that will turns out, that will be known as the equation. Okay, similarly this also. Okay, so here if you want to be more particular, neither y is there, so nor y dash is there, so it's essentially a function of t comma y double dash. Okay, or indeed it is a function of y double dash only. Okay, so t is also not explicitly occurs here. So I am just removing the things what are not appearing in the equation. Similarly here, in this case, if I want to write the general expression of the equation, this is going to be a function of t is not there, so I don't want to write the t. It's going to be y dash and y double dash. I want to use them only a variable. The rest of them I will ignore because they are constant. If that is a function of t, I will certainly mention. So these equation, if you see explicitly, they involve the first derivative, second derivative. This equation involves the first derivative and second derivative. This involves the only second derivative. Okay. So similarly, you can go with the third order derivative equation and so on. Okay. And also there may be chance that you will have some here powers. Okay. So maybe here at present with this application, it will not occur. But you may have some other application where you may have some power is, let's say, p. P may be integer, p may be fraction, any other thing. Okay. So if p is integer, that's also fine. If p is fraction, you have to get rid of this. Okay. How? Means like 1 by, suppose square root of dy by dt is there. So you take other things on the left side and keep it on the right side, and then take the square both sides. So you get rid of this fraction power. Okay. Necessary to define the degree of the differential equation, that we will also discuss a little bit later. Okay. So the general nth order ODE, so you can say nth order is why, because it here highest order derivative is going to be of nth order. So the previous differential equations, this and this both are of second order differential equations, because the highest order derivative is of order 2. So at present what we can observe from there. So if we want to relate with this equation, I think this is now clear. So here also one more thing is suddenly here x has been changed to t has been changed to x. So because we are going to consider here after y as a function of x only, so y is a function of x. Okay, and you have, this is y dash is denoted by dy by dx, y double dash as already mentioned, that is square y by dx square, y third derivative is equals to d cube y by dx cube, and so on. So now yn is equals to dny by dxn. So there are two type of notation. Here are the primes. You can also write this also. If I follow this notation, you can write y3. You can also write this as y2. You can also write sometimes y1. And this is also sometime for the sequence point of view, this also can be written by 0 sometimes. So y superscript 0 means there is no derivative performed, it's the original function. Okay, so be aware about these notations. Okay, so if you take any linear combination of this, so linear combination means the coefficients could be a function of x, any function of x could be a function of x or constant. Okay, if you take any linear combination of these and put them equals to 0, that will turns out to be an equation. So that is known as a differential equation. That's very okay. Moreover, linear combination means you have so I'm just giving you one example here. Suppose I'm taking let's say this is going to be y dash plus t. One linear combination is I have taken all of the coefficients are 1, y double dash, y derivative plus and so on, y nth derivative equals to 0. So that will give you one. This is simple nth order differential equation. Okay, now let me give you one more example where I'm just specifying the n value. Okay, so because it is not possible to work right now with the any general value here. So let's see, n equals to, let's say, for third order differential equation. So I'm just giving you one example more. So it's going to be, let's say, y plus x time y dash plus x square time y double dash plus x cube time y third derivative equals to 0. This is a third order differential equation. So we should ignore the coefficient if they are function of x only. Okay. Now I'm also mentioning that, well, when you are talking at general ODE, there is no restriction that only y dash and they should not be multiplied. So I just want to mention now that one more example of, let's say, so this is another example. You have, let's say, third example. I'm just taking n equals to, let's say, 2. Okay, right. So now I have one example, let's say y plus y into y dash. Okay, and you have, let's say, y second derivative square time x is equals to 0. So if you look at this is some function of y, x, y dash and y double dash equals to 0. So this is also a ODE. Okay, so it is not restricted that you cannot multiply y and its derivative, or you cannot put the multiplication among the derivative. That is also possible. Okay, so if certain things are there, these things are there, suppose multiplication of y and y dash are there, or any of its derivative, they are multiplied. Okay, so such equations are also called, I just want to mention here, non-linear. Okay, so that we will slowly be clear about it when we will say it's a non-linear or linear differential equations. So okay, so I'm just mentioning one example here because y into y dash is there. It's not a simple equation. That's what it means. Non-linear is not a simple equation. Okay, it's not easy to deal with this problem. Okay, right. Now another example is, let me take, so why this x only or x powers only? There could be any function of x. So this is also one of the equation. Let's say cos x time y dash equals to 0. Okay, so some trigonometric function also can be occur in the coefficient term. Okay, it's a first order, highest order derivative is first order derivative, and all of the power is 1. Okay, now let me take y only this trigonometric function of x only. I can take what is there is sine y plus y dash plus cos x time, let's say, y double dash is equals to 0. This is also a differential equation. This is a function of x, y, y dash and y double dash. This is also a second order differential equation. But what is specialty occur here is it's a function of, so y, or you can, instead of sine y, I can take sine y dash, or I can take cos y double dash. Okay, so there are, so if such things are happening, that also those equations are also known as non-linear equations. They are also not easy to handle. Okay, so I can comment only these much at present here. Okay, so when you take something very strange thing about the y and its y derivative, we can ignore the function of x. Okay, for deciding the order, you can say, and degree of the differential equation, but we can't ignore the term, okay, where the function of y is involved. Okay, so I hope you are aware about what do you mean by transcendental functions. I just this is a point of time I can mention transcendental functions. So all of the trigonometric functions, exponential function, logarithmic function, these all are called trigonometric functions. As simple as I just want to tell you, or in other words, What do you mean by this is, if a function, okay, that function, let's say f of x, can be identified as an infinite series. Okay, means infinite Taylor series, you can say. N equals to some 0 to infinity. You have this is Taylor series is f nth derivative at some x naught divided by n factorial time x minus x naught to the power n. So if a function has that infinite to non-terminating series, so such function is known as a transcendental function. In other words, I can say. So all exponential function, logarithmic function, trigonometric functions, all are having into this, falling into this category, straightforward. Okay, so if you take the product of them, also transcendental function. Okay, if you know any other function which has this infinite series, which is not a finite series, okay, then this also known as that will be known as a transcendental function. Otherwise, it is some algebraic function, you can say. Okay, so here you can see transcendental function of y is there, transcendental function of x is there. Okay, right. So this is the overview of general nth order ODE. Okay, if you equate them to equals to 0, if you take any linear combination, okay, then it will be done out. It will be, we will say that's the nth order, provided some conditions. So at present, you have not seen any unexpected thing. So here it is very easy. It's the nth order. It is very easy to see third order derivative is highest here. Okay, and this is a also differential equation where you can see second derivative is a highest order derivative present. Here is the first order derivative. Here highest order derivative is y double dash. Even though if you write sine y in the expression of infinite series, the highest order derivative is y double dash. It is still second order differential equation. Okay, right. Now let me have one more example. Okay, let's have, this is one more example. It's example number 6. Okay, so let's have this equation. Let me have, this is y dash plus let's say this is integration of cos x dx is equals to some x square, something like y into y is outside. So I want to so the very first thing I can tell you is this is a not a differential equation. I can tell you why, because it's not only involve the derivative, it also involve the integration somewhere. Okay, what I may feel here. Okay, now what we can do is I can certainly work out this integration term. Okay, now if I work out with this integration term, you know cos x integration is sin x. Okay, so I can certainly write y dash plus some sin x times y is equals to x square. Now this is in the proper form, you can say. Okay, so though this does not matter, this is, again, this turns out to be a function of x only. Okay, still we wish to solve it. Okay, and we will turn out in the simpler thing. So this is a differential equation now. Okay, and it can be seen that it's going to be a first order differential equation. Okay, right. Now, if instead of this, let's say another example is, let's say y dash plus cos x time integration of y dx is. Now, this is not a differential equation because it's not in simple form, because it also involves the integration. Now, another difficulty is what? You are integrating y with respect to x here. So, but y is unknown. This is unknown. This is unknown function. So you can't integrate and you cannot write a simpler thing for that. So what is the alternate here is you can use derivative. Okay, because which is the antiderivative, or you can say integral will get cancelled. So because integration is with respect to x, you are going to take the differentiation with respect to x. So you are going to differentiate both sides, okay, with respect to x. So then what you will get is d square y by dx square. Now using the product, you have to use the product rule here. So that's going to be something like cos x time integration of y dx. What is the derivative of this is y plus now integration of y dx time cos x derivative is minus sine. So minus sine x is equals to 2x. Now what you can do is, see, if you keep on applying derivative now, hereafter, so you have two equations. Okay, now you can eliminate this by equating this of these two equations, like because integration of y dx from here you will get some expression, from here also integration y dx will have some another expression. You can equate them and you will form a new equation. Okay, that will certainly not involve this integration y dx because you are going to remove this. So this is, if this implies integration of y dx is equals to something like x square minus y dash divided by cos x. And from here, this implies integration of y dx is equals to this is y double dash plus cos x y minus 2x divided by sin x. Now, since y is a solution of both the equations, it should satisfy both the equations. Okay, so certainly these two should be equal. And now you can you will be get rid of this. So you will be obtaining a simpler differential equation. Okay, and which is going to be which is a simple form where only y and its derivatives are there. Okay. Now highest order derivative, what will be the second order? So it's going to be second order differential equation. So certainly you cannot write from here this is first order differential equation because it's not a differential equation at first sight itself. So you have to get rid of this. So for getting rid of, you have to take one more step ahead, means you have to differentiate it. There is no other way. Okay, to eliminate this. Okay, right. Now another way is also what you can do is, I think one more way is there is you can write integration y dx is equals to this and then differentiate both with respect both sides with respect to x, and then you will also get one equation. So but it's going to be I hope so this is going to be a same equation. Okay, right. Now suppose I will write the same equation. Let's say another equation is, let's say example number 7, right? Okay, 8. So you have y dash plus, let's say, cos x time. Now integration of y, instead of dx, let's say this is dy is equals to x square. Though it is not a simpler form, but what you can do is, see, this is y integrating with respect to y. There is no role of function of x. So there is no requirement of derivative, differentiation. You can simply put the integration of y is y square by 2. That's it. So this is equivalent to y dash plus y square cos x by 2 is equals to x square. It's very simple. When you have integration y with respect to y itself. If you have integration with respect to x, then there is a trouble because y is an unknown function of x. Okay. So now this is a first order differential equation. Okay, right. So we have already seen is like this type of problems are there. So we can decide order of the differential equation at up to some level. Okay, right, fine. So what we have observed is from here. So observation, I can write as observations. So let me give you here itself observations. Or you can, in other words, you can say that this is a deciding order. Deciding order of body. Yes.
Sir, wouldn't there be a plus c with y square by 2?
See, when you are, see, this is This is talking about here constant. One constant is immaterial. Why? Because you can do that. Okay. But anyway, when you are going to solve this equation y dash, right? When you're going to solve this equation, that is also going to be, so if you sooner, I hope I may let you know that whenever you have a differential equation of, let's say, first order, then its solution will contain one arbitrary constant. So when you will have y dash, is a differential equation, when you solve it, that arbitrary constant occurs there itself. So you can start with working with here as well. It's not a problem, but I think it's here, it is not required to put the constant here. That's what I want to say here, because it's a first order differential equation. Now, if you have a second order differential equation, that will see here also. Okay, or in this case also, I can use, you may mention that why we have not here plus c. Okay, why? Because in the solution, when you are going to write the solution, that will take care of the arbitrary constant automatically. So in the differential equation, when you are performing some simple things, these things, so there is no requirement of putting additionally arbitrary constant. Okay.
Sir, hello, sir.
Yes, yes, yes.
Sir, if we apply question 6, question 6, method 7, then right or wrong? We both differentiate both sides.
See, in example 6, if you feel there is a requirement, then only you have to do, right? If there is no requirement of doing that, then we should not do it. We want to make it as simple as possible. That means simplified form, and we don't want to make our life to be a hell, right? See, solving a first order differential equation is rather easy than solving a second order differential equation. That's my point here. Now, see, if this coefficient, so this integral, you can simply replace it by sin x. Okay, so there is no requirement of derivative differentiation on both sides. If you do so, but that will convert it into a second order differential equation, that will become a very challengeable problem. Okay, so wherever, if you are able to perform the integration, these terms are known as a kind of radical terms. So how to get rid of them? So if it is possible to adjust with this equation itself, be if it is not possible at all, like here, it is not possible to be with it because you cannot go. And it's not a simple. Yeah.
I'm saying this is right or wrong.
Which one?
Question 6, if we differentiate both sides, I know not that this method is very good. I realize it is very long method, but it is right or wrong.
No, see, it is certainly, see, if you are going to ask in mathematically, I'm going to say you can do differentiation as many times as possible. You can go with the second order. You can again maybe differentiation at all. But what is the minimal thing that we can preserve that should be preserved? So it means the order will be decided with respect to, that means you can say in a minimal sense, you can say is like be with means like you can if you are able to work with a if you are able to make it as a first order differential equation itself, do it. Okay, that is only acceptable.
Okay, sir.
Okay, so if you can increase the order, that's, see anywhere, I have talked about many equations, so you can certainly go with the differentiation of the other term as well. So you can increase the order. There's no point. There's no problem with that. Okay, and then you will say, sir, this is now coming with n equals to 3. So this is suppose you are going to differentiate. It's going to be certainly with the third order derivative, and you say that's our order of differential equation is 3. What I'm interested in particularly is the order of this differential equation. I'm interested in this. You can go with the up to fourth order, fifth order derivative, and so on. So similarly here also, I want minimum what we can be with. Okay, we don't want to make our life hell, like you can say in other words. And if you will see soon that how it is challengeable to solve the second order differential equation if you are involving only variable coefficients are there. Okay, that is itself a very challengeable problems. Okay, if you increase the order, it's become a very tough question, tough answer. You have to, it will be very tough to answer that what is the guarantee that solution will exist. That's a very first thing. Okay, mathematically, it is very necessary to address that what is the guarantee that this does have a solution. If it has a solution, whether it is unique, that's the next question to that. Okay, so first
Sir,
order differential equation, second order differential equation, we can certainly talk about the existence and uniqueness, but for higher order, that also need to look at in some other algebraic form. Okay,
sir,
right? Yeah.
sir, if instead of cos x, if it was c dx, then the out means the final equation would be cxy, right?
Yeah, yeah.
So in that equation, do we have to consider c as an arbitrary? Means we have to differentiate once or not?
See, our plan is not get rid of any constant. Our plan is to get rid of any radical term. Radical term in the sense means if either it can be treated here itself, or it requires it requires some additional treatment. Like here, it is required to differentiate it. That's the only our goal. We should not worry about the constant and coefficient as a function of x only.
Okay, sir.
Okay.
Sir,
Yes.
sir, if we have an equation in the form of trigonometry and means cos y dash or sin y double dash, then we can't say the order of that.
That's what I'm coming now. That's what I'm coming now. Okay.
Okay.
So like here, I can certainly decide what is the highest order derivative present is second order. So I can say second order derivative. Now, what is the what will be what will be the possibility if suppose highest order derivative is not means like simple? It's going to be some tan inverse of y double dash. Okay, or some cos y double dash. Okay, so highest order derivative itself is not is coming as simple. It's going to be as a transcendental function, you can say, or y double dash square is somehow is fine, but have transcendental function of highest order derivative. Then how do you decide the order and the way that we can look at now? Okay,
Okay, sir.
Sir,
right.
I have doubt in example 7.
Yes.
Why haven't we considered here y as a constant? Like simply we could write x y. Like some many times we would use like cos theta into dx. Then
See when you are see in the equation you have y dash. Okay, the very first thing. The another thing is you are knowing that y is a function of x. Y is some function of x, and that is unknown to you. It's not a constant. If it is a constant, see, if instead of dx, if you have a dou x here, partially integration with respect to x, that's something different case. We are talking about when you have partial integration with respect to x.
or it could be dt. If there would be dt, then you can say like y dt, yt.
So dt means what? Why dt means you are introducing one more new variable. Means like already x variable is there. Y is variable. Y is a function of x, and you are saying here dt.
Yes. And
Or you are changing x equals to t.
no, new variable. If it
No, it's a problem of now. I think one, two, three variables. I think so, and or y is a function of x comma t. Or suppose you know that y is a only function of x, and you are integrating with respect to t. Then it is certainly t time y. There's no question about it. If you are sure that y is a function of x, but if it is given that y is a function of x as well as t as well, and it is unknown, so you can't do that as well. Okay, right. Since it is unknown here, so you have to be careful. Okay, right. So we can decide from here. So deciding order of, let's say, first order of ordinary differential equation. Okay. Now, first, okay, let's first observation is you can say we are going to decide the order only. Okay, an order of ODE is the order of the highest derivative of the highest derivative present in ODE. So I'm going to add something here. So an order of ODE is the order of the highest derivative present in ODE after removing fractional powers and radical terms. I have already mentioned you what are the radical terms, those type of integration terms. Okay, so order of ODE can be decided as the order of the highest derivative present in ODE after removing fractional power and radical term. Radical term present in the original, you can say original ODE or original equation. I should not say ODE because it may be a integration of y dx and which is not a ODE, it's going to be integral differential equation in some other way. Okay, so here you see the seventh example, this is integral differential equation because this integral involves an integral of unknown function. So it is not in the form of ODE. So wherever we have talked so far, not talked any fractional power, you can do that. Okay, so let me give you one example here, fractional power, how do you remove it? So example number 9, yeah. So let me consider this y dash plus 9x y double dash to the power, let's say 1/3 is equals to 0. I think for my side as well, I'm considering random examples, so sometimes it will be a problem for me as well sometimes because randomly chosen problem may not be a well-posed problem. So sometimes it will be difficult. Okay, so I'm choosing it. So from here, so to get rid of this fractional power, so I can certainly write y double dash to the power 1/3 is equals to minus y dash by 9x. Now you cube both sides, so that will be y double dash is equals to minus y dash cube, and this is going to be 729x cube. So this will imply. So now equation is y double dash time. Okay. So the final equation is, so this implies 729x cube time y double dash plus y dash cube is equals to 0. So this is the form which we want. Okay, so here highest order derivative presents, there is no radical term, so we don't worry about it. So only now this I can decide here is order of this differential equation. Order of given ODE, you can decide certainly, is equals to 2. Okay, I will come back to this question again. Okay. Now let's consider another example where the highest order derivative occurs as a transcendental function. Okay, so let's say this is a 10, or you can say instead of 10, let me say sine. Okay, sine of y dash plus let's say cos xy is equals to 0. It's a simple equation. I mean, simple means in terms of y dash only. Now, if you consider, see, sine y dash, you can write as a infinite series. So that's going to be y dash minus y dash cube by 3 factorial plus y dash to the power 5 by 5 factorial minus y dash to the power 7 by 7 factorial and so on, plus cos x time y equals to 0. So there is no harm to write this infinite series because this is a convergent series. Okay, we know that. That's a convergent series. It's an infinite series. This converges for every value of x, sin x, you know, right? Okay, so we don't worry about that. Why you can put dot 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 here. Okay, so meaning is this is a meaningful term. Okay, now if you see, what is the highest order derivative present in this entire equation? It's still first order derivative. Whatever the ending term it is goes, it involves y dash only. Nowhere the derivative is changing. Okay, so certainly here I can write order is 1 because in none of the term you don't have any because you can decide very easily from here that whatever term you write down, any nth term you can say, it still have y dash to the power, integer power only. Okay, and highest order derivative is 1 only, so I can decide order is 1. Now let me consider example number 11 now. So instead of this, let's say y dash plus, let's say, cos x times sin y. Suppose this is there. Okay, now so you can certainly write it into y minus y cube by 3 factorial plus and so on. But it does not matter because highest order derivative present here is 1 only. Okay, so still order is 1 here. Okay, now if you have cos y dash here or e to the power y dash, you write the Taylor's form. Okay, so still it has the first order derivative, only the highest order derivative present in the differential equation. That order is 1. Okay, so this is what I can answer you regarding your transcendental function of y or its derivative is present in the equation. Then how do you decide the order? Now second observation, which is very important. So second, now you have, which is called as known as the degree of the, that's also very important, degree of ODE. The statement will be almost the same only. Okay, the degree of ODE is the index of, or you can say not index, instead of index I should write here highest index or power, you can say highest index or power of highest order derivative. Present present in highest order derivative in let me write it some more appropriately. So highest index or power of highest order derivative in ODE obtained from original ODE, means which one is original equation after removing fractional powers and radical terms. Okay, so in an ODE obtained from original equation which is given after removing fractional powers and radical terms. So let me decide now from the first question itself. Let me see how we will be able to decide what is the degree of the ordinary differential equation. I hope you are now comfortable with what do you mean by fractional power and what do you mean by radical terms. Okay, right. So let me go with the equation. So here the highest order derivative is present in an order derivative, and or none of the power is fractional power. All of the power is one in the integer only. Okay. Now highest index of nth derivative is 1 only. So here degree is 1 and order is n. So I will denote d by degree and o by order for this equation. Now in the second example here you can see, so note that we are only worried about y and its derivative. So you can certainly ignore function of x in the radical terms as well sometime. Okay. For if you are working only means like gate type problems, it's like there you have to answer only for MCQs. So that's a kind of shortcut you can say. Okay. But when you explain in the subjective questions, you have to get rid of that radical term and then you have to write final answer. Okay. Right. So here you can see that y and y dash and y double dash and y third derivative. So we don't work. So we are not worried about the fractional power. Or suppose there may be a chance that is the square root of x here. We are not going to get rid of this function of x here, square root of x or x power, fractional powers. We are only worry about the powers of y and its derivatives. So I should mention it in the observation. So I will mention it again. Okay. So we are only worry about the index of the y and its derivative. We are not worry about the function of x or transcendental function or it is going to be a power is fractional power or anything. We are not worry about the function of x. Function of x means explicit function of x. Means it's not like y is also a function of x, so I should not care about it. Yeah.
If there is a root y, then it will make no difference.
It will make difference.
So
if
we
there is
have
root
to
y,
remove that root in y.
yes, yes. So I'm again telling you you have to worry about the index of the y and its derivatives. If they are not of integer, or you can say they are not a positive integer, in other words. Okay, so you have to get rid of that. Okay, fractional power. So like we have done in some example. Okay, so we are only concerned is y and its derivative in terms of fractional powers. We are not concerned in the function of x. It may be cos x to the power 1 by 2, root cos x as well. It's fine, completely fine. Okay, so I will I will write down some more examples. So let's wait for some more time. So here it is very clear that y and its derivative and there is no fractional power. So you can decide certainly the order is free and degree, highest order index, highest index of the highest order derivative is here. So degree is 1. It's a third order differential equation of first degree. Okay, let me go with the third question now. Now, if you look here, y and y into y dash, and if you look at each term, there is no fractional power. And what is the highest order derivative is 2. So order is 2 and it's a simple differential equation. There is no need to remove from fractional power or any radical term. So order is 2 and the highest index of the highest order derivative is 2. So that is degree is also 2. So this is second order, second degree differential equation. Okay. Now the example 4. Okay, it's the order 1 and degree is 1 because the highest order derivative is first derivative and its index is 1. Okay, we are not worried about the transcendental function of x here. So cos x you can write in terms of infinite series, right? X 1 minus x square by 2 factorial plus x power 4 by 4 factorial and so on. And you say that sir x power is not defined, so I cannot define degree. No, we are only worried about concern about y and its derivatives indexes. Okay, or in particular we are only interested in the index of the highest order derivative. We are only should be careful for the index of the first highest order derivative. Like in the next example here, if you look at, as already discussed, this here sine y if you write in that infinite series, it has y and y its powers, and powers are integers only, y cube, y power 5, odd powers you can. Okay, but our concern is to see the highest index of the highest order derivative present in the differential equation. So, but y is not a highest order derivative here. The second derivative is the highest order derivative. So here index is highest order derivative is 1. And order is highest order derivative is 2. So it's order 2 first degree. Now let me have here. Now here, after removing from radical terms, so this is a radical terms, you can fix it by replacing it by sin x. Now this is very simple to get it. So order is 1 and degree, highest order derivative is first order and highest index is 1. So order 1, degree 1. Okay, now look at here. So this is not acceptable. You have to get rid of this, and which will be turn out to be it means if you equate these two, it's going to be turn out to be a second order differential equation. I hope you should be with me if you write in the simpler form. Okay, and if you arrange everything, so highest order derivative is second order. Okay, if you are going to means like left and means you take the denominator from left to right and right to left. Okay, and so on. So it will not affect the index of the highest order derivative. So you can simplify it. Order is 2 and degree is 1 for this case. Similarly, let me come back here. So here, this is a simple form. This also can be fixed by replacing y dy, integration is by y square by 2. Now, here highest order derivative is y dash, the first order derivative, whose index is 1. So order 1, degree 1. Okay, right. Now, let's come here. Okay, now add the fractional power now. So you have to get rid of this fractional power. Okay, then you have this equation now. So here order already we have decided 2. So highest order derivative, highest index is 1. So it is of degree 1. We are not worried about y dash cube is there, so it's a cubic equation. Okay, it may be cubic equation in y dash, but it's not a cubic equation in y double. We are only concerned about the highest order derivative index. We are not concerned about this. Okay, right. Now the next example here. So now here, if you write into the this is going to be right in the Taylor series form. So y dash, and you see y dash powers are means increasing here. So the increasing, right, 3, 5, 7, and you don't know what is the ending term. So you cannot decide here degree, because see here the highest order derivative is y dash in this equation. Okay, and whose degree means highest index of this y dash cannot be find out. So we cannot decide what is the highest order index, means infinity. It is infinity. It's a very large, huge number. So degree cannot be defined for this. Degree cannot be defined. So if the transcendental function of highest order derivative present in the differential equation, so for that case degree cannot be defined. But here is not transcendental function of highest order derivative. It is a transcendental function of y, and highest order derivative is y dash. Okay, so here you can decide the degree is 1. So it's a first order, first degree differential equation of degree 1. Okay, so here, this is in order of the highest derivative present in the ODE after removing fractional powers and radicals term present in the original equation. Okay, fractional powers you can see of y and its derivatives. So we only y and its derivatives here. We are only worried about this fractional powers of y and its derivatives. We are not worried about function of x. Okay, if present. And similarly for that observation, after removing fractional powers of y and its derivatives. So okay, let me write down of y and its derivatives. So this is clear here that we are nowhere worry about the coefficient as a function of x. Okay, for deciding the order or deciding the degree of the any differential equation. We are only concerned about y and its derivative. Okay, right. Now the third concern is when you will say a given ODE is linear or non-linear. Okay, so third observation means we can say ODE is linear. If I give you that, say, means how to decide whether linear or not. So if I answer you, if you are able to decide that not, it means it's not satisfy one of the condition there, what I'm going to mention. Okay, then it is fall into a non-linear. So that otherwise it is non-linear. If it is not linear, it is a non-linear differential. Okay, right. Okay. So an ODE, okay, means like the statement follows here obtained from original equation. Again and again I want to mention here so that it should be clear. So obtained from original equation after removing fractional powers of y and its derivatives, and radical terms okay, and ODE, so I am making it here bracket here. So an ODE obtained from original equation after removing fractional powers of y and its derivatives and radical terms is called linear if it satisfies following three conditions. Means all of the conditions should satisfy. It looks like maybe difficult to verify, but they are very easy to verify when you a little bit practice it. Okay, so let me write the first condition. Let me write in Roman 1. Okay, no degree of all of y and its derivatives, or let me write it in other words. Y and its derivatives are of degree 1. Means you see in the means kind of scanning. You can go to you are scanning a different, means you are given with the differential equation, means you have removed all the fractional powers from y and its derivatives and remove all the radical terms, then obtain OD. I'm talking about that. Now you scan it, means like you just look at it. Okay, and what you first observation you have to do is y and its derivatives are of degree 1. Means wherever you see y and its derivatives and its indexes, then you have to see their indexes. then they are of degree 1. Means neither it should be 2 or 3 or 4 or and so on. Okay, there should not be y square, there should not be a y dash whole square, or there should not be y double dash whole cube, and so on. I'm talking about that. Okay, we are not, again, I'm telling you, y and its derivatives are of degree 1 means we are completely ignoring the coefficient as a function of x. Okay, we are completely ignoring the function of x. Okay, means when you are scanning the equation, you can just put a white mark on the function of x. Okay, only see, look at the carefully y and its derivatives. Okay. No product term of y and any of its derivatives present in OD. What it says is, it's not, you should not consider it like y and its derivatives, means y into y dash or y into y double dash or y into y third derivative. So it means that y and any of its derivatives means any two pair or any three pairs from that set. Means it may be possible y dash into y double dash. Y is not there, so you should not say that, okay, this is like, you have to be careful. No product term of y and any of its derivative present ODE means y, you take a set y2, y another derivative, y dash, y double dash, you choose any two from there, so product term should not be there of them. So kth derivative into yk minus 1th derivative, or ykth derivative into y function. Okay, not consecutive one also cannot be possible. So no product term of y and any of its derivative present in ODE. That's the second condition. That also very easy to identify. Then third condition is, no transcendental functions. No transcendental functions of y and any of its derivatives present in OD. Means, again, see, in the second condition also, in the third condition also, you will see you are completely ignoring the coefficient as a function of x or constant. Okay, we are not caring about, they are putting the white marker. Okay, we are not care at all. Okay, only caring is the set y and its derivative. So here the third condition says that no transcendental function of y is like sine y, cos y double dash, or tan of y dash e to the power y. So if you find that in the equation any transcendental function of y is present, it is a linear differential equation. If you find that any of the product, means any term means each term is like addition. Okay, means where you have n terms or so, I think you can that will be familiar with that meaning, that what is the meaning of term. So each term, if any of the term will consider product of y and any of its derivative, so straightforward, it is a non-linear. Okay, if any one of them, y and its derivative, okay, has the degree not equals to 1. Okay, it may be -1, it may be means like -2, it may be -3, or it may be 1/2, it may be 1/3, or it may be 4. So you have to get rid of these things. Okay, and then you can see that that's going to be if they are not of degree 1 in the same obtained equation, then it is going to be a non-linear differential. Now let's go back and check our differential equation, which we have mentioned whether they are linear or not. Okay, based on these three conditions. So let me go with the first example. Yes, so here y dash y double third derivative, y-nth derivative are of degree 1. All terms. So this is first term, second term, third term, fourth term, and so on. These are the terms. N term, nth term. Okay, all of degree 1. So all y and its derivatives are of degree 1. Okay, you should not say, sir, there is y to the power 0 is also there, so 0 is not equals to 1. We are not here to make that here. Okay, right. So I suppose here is equals to 1. Suppose it is equals to 1. It will also not change. You cannot take it as y to the power 0. It may be x to the power 0. Okay, it's a constant, fixed. It's not a function of y at all. Okay, right. So all are of degree 1. That's the first condition is satisfied. Second condition is none of the term has product of y or any of its derivatives. Okay. Third condition is no transcendental function of y. So it's a linear. So this is a linear differential equation. So linear nth order first degree differential equations. Okay. Now this second question here. Now see the y and y double dash and y third derivative. They are only present. Y dash, y double dash, and all are of degree 1. No product term. And in each term there is no transcendental function. So this is also a linear. As I mentioned, you should completely ignore the function of x coefficient. Okay, so there is no point of talking it x square or x cube. So it is not says that it's not a linear. Okay, it's a linear because we are not worried about these powers, x powers. We are only worried about y and its derivatives. Similarly, for this case here, so here you can see the first term has y of degree 1, but immediately you can check second term has the y and its derivative, product term is there. So it's a non-linear. It's a non-linear. Then I will go to check the third term. Okay, because once it is verified with the second terms, I will not go for scaling further. Okay, if suppose this is y dash only, if there is no y, then I will check with this y double dash. So square is there, so power is not 1. So it's also still a non-linear. Now in this case, example 4, derivative y dash, they are of degree 1, no product, no transcendental, say linear. Here, so transcendental function of y is present in the first term itself, so it's a non-linear. I can certainly say from here itself non-linear. Maybe other term may satisfy other conditions, but first term is not satisfying, so it will tell you that it's a non-linear. The others, as so I just mentioned here, this is a linear. Okay, now here if you do this, this is a cos x into y. Okay, if you do this, this is also going to be a linear. Yeah, this is going to be a linear equation. Okay, right. So just go and check at home as well as say non-linear. I can comment here because y square is there, y to the power 2. It's not 1. So you put the white mark for on the function of x and coefficients. So here also this is see y double dash are of degree 1. This y dash to the power 3 is a non-linear. Okay. This is a non-linear. Okay. This is also a non-linear. Because transcendental function of y present. Okay, right. So we have now, if any of the condition is not satisfied, so I can just mention and then complete it. If, and I think I should write here or, then it will be very clear y or any of its derivatives. So if any of the above condition fail, any one of the above condition fails, then we say that the ODE is non-linear. Okay. So we are completing here. Okay.